In quantum theory, the Heisenberg uncertainty principle states that it's impossible to determine both the position and velocity of an object simultaneously. Because electrons are constantly moving, it is impossible to accurately measure their exact positions. However, when you plot their positions many times, you'll begin to see the space where an electron occupies 90% of the time, known as an orbital. An orbital is a three-dimensional region around a nucleus where the electron likely occupies. These orbitals exist in different shapes and sizes. Quantum numbers specify the properties of atomic orbitals and the electrons that occupy them. The first three quantum numbers indicate the energy level, shape, and orientation of an orbital. The fourth quantum number indicates the spin of a specific electron within the orbital. Each orbital consists of two electrons, one that spins upwards and one that spins downwards. Electron configuration is a form of notation that details the distribution of an atom's electrons across energy levels at varying distances from the nucleus. The first step in determining an atom's electron configuration is finding out how many electrons are present. In an atom, the number of electrons is equal to the atomic number, or the number of protons. Electron configuration only tells you about electrons. If a carbon atom, which usually has 3 more electrons than an atom of lithium, had a positive 3 charge, its electron configuration would be identical to that of lithium's. This is helium's electron configuration. The 1 refers to the energy level, which is the shell it can be found on. The principal quantum number for an electron's energy level is n. The s refers to the sublevel the electron is in. Sublevels contain orbitals. The different sublevels are s, which is spherical and contains 1 orbital, p, which is dumbbell-shaped and contains 3 orbitals, d, which contains 5 orbitals, and f, which contains 7 orbitals. The d and f sublevels are a little harder to visualize. The 2 refers to the total number of electrons in that sublevel. For the first 4 energy levels, the number of sublevels that the level has is equal to the number of levels. All other levels above that have 4 sublevels. The first sublevel is S, the second is P, the third is D, and the fourth is F. To summarize this explanation, the first energy level consists of an S sublevel, which means it can only hold a maximum of 2 electrons. The second energy level consists of both S and P sublevels, meaning it can hold a maximum of 8 electrons. The third energy level contains an S, P, and D sublevel. Therefore, it can have up to 18 electrons. The fourth and all higher energy levels contain an S, P, D, and F sublevel, making for a maximum of 32 electrons. Atoms naturally try to work their way towards stability, as we discussed in my last video. This means that atoms try to work towards the lowest possible energy because the high energy systems are unstable. This is the order in which electrons fill in energy levels. Notice how in some scenarios, an energy level will begin before its predecessor is completed. This is because the atom naturally tries to fill its energy levels with the least amount of energy as possible. It's easier to fill 4s with 2 electrons than 3d with 10 electrons. When mapping out electron configuration, we abide by 3 rules. The first of these rules is the Aufbau Principle, which states that electrons begin filling orbitals at the lowest energy. The second rule, which is the Pauli Exclusion Principle, states that no 2 electrons can have the same quantum numbers. We distinguish between the 2 electrons in an orbital with the 4th quantum number, which identifies the spin of an electron. The third rule is Hund's rule, which states that when electrons enter orbitals of equal energy, each orbital is filled with a parallel electron, before the orbitals fill up with electrons with complementary spins. Let's look at an atom of tin. Tin has 50 protons, and thus 50 electrons. If we were to determine the electron configuration of tin, we would find it to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2. Now let's look at the electron configuration of the periodic table. Notice how the table's shape is organized by the sublevels of electron energy levels. The valence electrons are always the sum of the electrons in the highest energy level. This is why potassium has 1 valence electron in the 4th energy level, despite it not yet reaching its full capacity of electrons in the 3rd level. A shorthand way of notating electron configuration is via noble gas notation, where you cite the preceding noble gas's symbol in brackets and write out the rest of the electron configuration normally. This is lead's electron configuration written out, and this is lead's electron configuration in gas notation. Sometimes an electron will have enough energy that it will jump to a higher level than usual. This would be the atom going from a ground state to an excited state. The unstable excited state would return to the more stable ground state, but only after giving off the energy in the form of heat and light. Longer wavelengths means a lower frequency, and therefore, less energy. Shorter wavelengths means a higher frequency and more energy. Red light has longer wavelengths, and violet has shorter wavelengths. Contrary to common belief, violet is a hotter color here, because it has more energy. In this excited state, the element's electron configuration does not follow the Aufbau principle. You'll see that a higher sublevel of electrons can begin before a previous one is completely finished. Each element has a special spectrum emission, which can be used to identify it. This is because every element has a different energy requirement to move between electron energy levels. So to recap, we learned what quantum numbers are and what they tell us, electron energy levels and sublevels, and electron configuration and the rules that it follows. We also learned that electrons can be in an excited state and give off light when its high energy electrons return to ground state. The next video will be on bonding, and you can find a link to my chemistry playlist in the description.